Assalamu alaikum. In the first problem, you have a mass of 1.5 kg of air. So mass is m is 1.5 kg, and the pressure is 120 kPa, and the temperature is 24 degrees Celsius. So this air is contained in the gas-tight frictionless piston cylinder device. So you have a piston cylinder device in which you have a gas having a mass of 1.5 kg and the pressure of 120 and the temperature is 24. The air is now compressed to a final pressure of 600 kPa. This is P1 and this is T1 while this is P2. During the process, heat is transferred from the air such that the temperature inside the cylinder remains constant. So this is constant temperature isothermal process. So you have to calculate the work input. Okay, so on PV diagram, the isothermal line is represented by this way. You are going from position 1 to position 2 while temperature remains constant. So you have to find the work. So the formula of the work is W is equal to mRT log of P1 by P2. This formula is similar to this formula. W is equal to RT log of P2 by P1. So for isothermal process, you will use this formula. So this is mRT. Because the mass is given, you have to put mass here and you have to use R in this unit, kilojoule per kg per Kelvin. So if the mass is given, you have to use use the R in the units of kg. Okay, put 1.5 kg for mass, 0.287 for R, 297 is the temperature in Kelvin, 24 degrees Celsius is the temperature. So when you are 273 to it, this degree Celsius will be converted into the Kelvin, which is equal to 297, while log of P1 by P2. So P1 is 120 while P2 is 600. So your final answer will be this 206 kilojoule. Now the next question is during some actual expansion and compression process in piston cylinder devices, the gases have been observed to satisfy the relation. So this is polytropic process. PV raised to power n is equal to C, where n and C are the constants. You have to find the work done when the gas expands from pressure of, this is P1 and this is volume V1 to final volume of, this is final volume V2 for the case in which n is equal to 1.5, and you have to find the W, work done. So you don't need to draw any diagram for this problem. So for a polytropic process, we use this expression. P2 is equal to P1 V1 by V2 raised to power n. So n is 1.5, which is given. V1 is 0.03 while V2 is 0.2. Just put the values and multiply it with P1, you will get your answer. So this is for P2. So in order to find the work, so in polytropic process, the expression for work is this: P2 V2 minus P1 V1 or 1 minus n. Okay, so n in this case is 1.5, while you know P2 from this formula. V2 is given, P1 and V1 is also given. Put the values here, you will get the answer for the work. Next question is, you have a frictionless piston cylinder device. This is piston cylinder. It contains 5 kg of nitrogen at 100 kPa and the temperature is 250 Kelvin. Nitrogen is now compressed slowly according to the relation. So this is the relation. This is also a polytropic process until it reaches a final temperature of 360 Kelvin. So this is T2. You have to calculate the work. So in this case you will use this formula: W is equal to m or T2 minus T1 over 1 minus n. These formulas are available in your book. Let me show you the book. So this is the book, and this is adiabatic process, and this is polytropic process. As you can see, the formulas for the polytropic process are given. So in case of polytropic processes, you use n in place of this gamma. So in this presentation I have used this formula mRT2 minus T1 over 1 minus n. Okay, just put the values. M is 5 kg, R is 0.2968. So for nitrogen, the value of R is different. In the first example, we had air. Okay, so for air, the value of R is 0.287. The value of universal gas constant is 8.314 joule per mole per Kelvin. Okay, so this is always this a universal value. So for if you want the value of R for air, you know that the molecular weight of air is 29 gram per mole. Okay, you will just do is divide this 8.314 divide this term by 29. So I am writing here 29 gram per mole. So this mole will be cancelled with each other. You will get your answer in joule per gram per Kelvin, and further you can convert this gram into the kg. 1000 gram contain 1 kg. Okay, this is unit conversion. You can do it by yourself. So far, in case of nitrogen, then the molecular formula of nitrogen is 28. So you can do this conversion by yourself. Just put the values. T2 is 360, which is given, while T1 is 250, and 1 minus 1.4. Just put the values, you will get your answer. In this problem, you have an ideal gas initially at the temperature of 600 Kelvin. So T1 is 600 and the pressure P1 is 10 bar. It undergoes a 4-step mechanically reversible cycle in a closed system. Okay, there are 4 steps. So in the step 1 2, in step 1 2, pressure decreases isothermally. So 1 2 process is isothermal, which is written here. So 1 2 process is isothermal, and the pressure is reduces to 3 bar. In step 2 3, pressure decreases at a constant volume to 2 bar. So the press 2 3 is constant volume process, which is isochoric. In step 3 4, the volume decreases at constant pressure. So 3 4 is isobaric process. So the pressure remains 2 bar for the 3 4 process, and in step 4 1, the gas returns adiabatically to its initial state. So 4 1 step is adiabatic process, and you are going back to your initial state. Okay, so Cp is 7 by 2 R while Cv is 5 by 2 R. You have to sketch the cycle on PV diagram in part A. In part B, you have to determine where the unknown both T and P for the state 1 2 and 3 4. You have to find that T1 T2 T3 T4, okay, and P1 P2 P3 and P4, and you also have to calculate Q W delta U and delta H for each step. So first I am going to solve for adiabatic process. So the data is given in step 1 to 2. It is an first I write here T1, which is 600 Kelvin, okay, and P1 is 10 bar. In step 1 to 2, the pressure decreases isothermally to 3 bar. So in step 1, this is state 1. So state 2, so temperature remains constant, so T2 will be similar to the state 1 because this is an isothermal process, while P2 will be 3 bar. No, in step 2 to 3 pressure decreases at constant volume. So so 2 to 3, this is isochoric process, and the pressure becomes 2 bar. So P3 is 2 bar, while you don't know what is the value of temperature. So T3 you don't know what is the value of T3. And in step 3 to 4 volume decreases at constant pressure. So P4 remains constant, so which is equal to 2 bar, while you don't know about T4. And in step 4 to 1 the gas returns adiabatically to its initial state. So if you go from back to here, this is an adiabatic process. So first of all we will solve the adiabatic state. So for this the formula is this: T4 is equal to T1. Actually I am using this formula from the book. Let me show you. So this is a book, and this is formulas for the adiabatic process. So I am using this formula. Okay, so T2 here means final temperature, T1 means initial temperature. So in our case the final temperature is 1, state number 1. So and the initial temperature is 4. This is initial, because you are going from 4 to 1, so you will write your formula according to it. Actually the formula was T2 by T1 is equal to P2 by P1, but here you will write it like this: T2 by T1. So T final temperature is T1 by T4, which is equal to P2 by P1. So P2 is P1 and over P4 raised to power R over Cp. So this expression is similar to this one. Just take the inverse on both sides. You will get the similar form to this formula. Okay, so T4 is equal to T1 into P4 over P1 raised to power R over 4. So put the values. T1 is 600, P4 is 2 bar, while P1 is 10 bar. So it will be equal to 2 by 10, while T1 is 600 R over Cp. So R over Cp means it is equal to R over Cp is 7 by 2 R. 7 by 2 is 3.5 into R. So it will be equal to 1 over 3.5. Just put the values, you will get your answer for T4. Okay, in order to find the delta U for adiabatic process is CV delta T. Okay, it is like this: CV T1 minus T4. Just put the values, you will get your answer. The value of R is 8.314 joule per mole per Kelvin. For delta H you will use Cp T1 minus T4. Put the values. Cp is 3.5 R. 3.5 into R. Cp is 3.5 into R. Okay, just put the value for R 3.5. R is 8.314 joule per mole per Kelvin. 3.8.314. While for CV is 2.5. 5 by 2 is 2.5 into 8.314. Okay, you can find it by this. For adiabatic process, Q is 0, while for adiabatic process, work is equal to delta U. So that's how you will solve it. Now this last thing is volume. You will find the volume uh, by using ideal gas law. V2 is equal to RT2 over P2. Okay, so everything is clear. So T4 or T4 was equal to 378 Kelvin. Now we will solve the step number isothermal process. For isothermal process, delta U is equal to, you know that delta U is equal to CV delta T. Delta T is 0, so this term is 0. Delta H is equal to CP delta T. Delta T is 0, so delta H will also be 0. For Q, you will use this formula minus RT log of P2 over P1. Okay, you are going from 1 to 2. So temperature T1 is 600 Kelvin. You will write here R is 8.314 and temperature is 600. P2 is final pressure. 1 to, you are going from 1 to 2. So 2 is your final state while 1 is your initial state. So final P2 is 3 bar. I have written here. So log of 3 by, while P1 is 10 bar. So just solve this equation, you will get your answer. So in isothermal case, W is equal to minus Q, because you know that delta U is equal to Q plus W. So for isothermal process, this term is 0. So W become equal to minus Q. Now the next step is isochoric process. So for isochoric process, delta U is equal to CV T2 minus T3 minus T2. CV is 5.2 into R is 8.314. Just put the values. The value of T3 is unknown. So T3 is unknown so far, which will be calculated by using ideal gas law. T3 is equal to P3 V3 over R. Okay, so P3, what is the value of P3? P3 is 2 bar, while V3, you don't know about V3. While it is equal to V2, you just determine here V2 is equal to RT2 over P2. You know the value of T2 and the value of P2. Just put here, you will get the V2. So V2 is equal to V3 because 2 to 3 is an constant volume process. So that's why V3 is equal to V2. Put the values, you will get 400 Kelvin. P3 is 2 bar. So here you will write 2 into 10 raised to power 5. V3 is equal to V2, while V2 was equal to 0.017. Just put here 0.017 for V3, and for R you will write 8.314. This 10 raised to power 5 is for the conversion. I have converted bar into the pascals. So for CV is 5.2 into 8.314 multiplied by this 400 minus T2 is 600. I just write here 5 by 2 into R is 8.314, while T3 is 400, while T2 is 600. Just put the values, you will get your answer. This will be your answer. So for delta is Cp delta T, just 7 by 2, 8.314, and the rest is same. For Q, it is equal to Cv delta T. It is similar to this one, delta U. And for isochoric process, W is always 0. In order to find the T4 for V4, you will use the ideal gas law. So V4 is equal to RT4 over P4. Put the values, you will get your answer. T4 is 378. We have calculated in adiabatic process. The T3 is 400 Kelvin. Let me write here. Okay, isobaric process, delta U is equal to Cv delta T. Cv is 502 into 8.314. T4 is 378, while T3 is 400 Kelvin, which is given here. Put the values, you will get your answer. Delta H is Cp T4 minus T3. Put the Cp value, T4 and T3, you will get your answer. Q is equal to Cp T4 minus T3. The answer is similar to the delta H. And for W, you will use this formula RT4 minus T3. The value of R is 8.314, while T4 is 378 and T3 is 400. Next question is, the state of an ideal gas which Cp is given 5 by 2 over R. So Cp is equal to 5 by 2 over R. You asked me about how to calculate Cp. So Cp is equal to 5 by 2 R. The value of R is this. So 5 by 2 is 2.5. Okay. So just multiply 5 by 2 with this. You will get your answer for Cp. Okay. So pressure P1 is 1 bar. V1 is 12 meter cube. P2 is 12 bar and V2 is 1 meter cube. In the first step, you are following the isothermal compression, and you have to find the Q, W, delta U, and delta H. The formula for work is nRT log of P2 over P1. Okay, so you know that PV is equal to nRT. So that's why I have written here P1 V1. Value of P1 and V1 is given. Always use the absolute units. Convert 1 bar into that Pascal, which will be equal to 10 raised to power 5 Pascal. So you have to put here the Pascal. Okay. So if you are putting the Pascal here, you will get your answer in the joules. So your answer will be 2982000 joule. Okay. You always use SI units. Your answer will also be in the SI unit. V1 is 12 meter cube log of P2. P2 is 12 divided by P1 is 1. Just put the values, you will get the answer for the work. For isothermal process, delta U and delta H is equal to 0, while Q is equal to minus work. Work you have calculated, so Q will be equal to minus 2982 kilojoule. So this was the first step, isothermal process. So in the part B, first there is adiabatic compression, which is followed by the cooling at constant pressure. So first you will compress the ideal gas adiabatically. Okay, so for calculating the work, you will use this formula. So you have to find the P2 P2. You know the this V, you don't know what is the value of this Vi. Okay, because you are pressing your ideal gas. You don't know the intermediate volume. So first you will find the intermediate volume, because this step involves this step is divided into two sub steps. Like first of all, you are going to compress your gas. Let's say you have a gas and you compress it adiabatically, and it reaches to some intermediate state, and then you cool this then you cool it at constant pressure, then you put the pressure constant. For example, in the first state you had the pressure P1, and you compress this gas adiabatically by keeping the Q is equal to 0, and when you reach at this intermediate state, the volume become Vi. Okay, you don't know what is the value of this Vi, and the pressure become P2. Okay, and thus you in the second substep you cool this gas. Okay, so first of all, if you are applying the work formula, you have to use the volume, intermediate volume. Okay, so intermediate volume will be calculated by this formula. Put the values. Gamma is 5 by 3. Why 5 by 3? Because first of all, you know Cp value. Cp is 5 by 2 R. Okay, let me show you from the book. So from the book, you know that Cp is equal to Cv plus R. So Cp is equal to Cv plus R. So in order to find the Cv, so Cv will be equal to Cp minus R. Okay, and Cp is 2.5 R. 5 by 2 is 2.5 minus R. So 2.5 minus R will be equal to 1.5 into R. So it will be equal to 3 by 2 R. Okay, gamma is equal to Cp over Cv. Cp is 5 by 2 R divided by 3 by 2. Okay, so 3 by 2 will be written like this, 3 by 2 R. So this will R will be cancelled, 2 will be cancelled with each other, so gamma will be equal to 5 by 3. Okay, put the values in these formulas, you will get your answer for Vi. So put the values for Vi, you will get the work answer. Okay, in the second substance you are going to cool at constant pressure. So at the constant pressure you will cool, so you will use this formula, minus P2 into V2 minus Vi. Okay, so pressure P2, put the value of pressure. P2 is this 12 bar. Okay, put 12 bar. So always use the SI units, convert the bar into the Pascal. V2, you know the V2, what is the value of V2? And at the last Vi. So value of V2 is this 1 meter cube. While because you are cooling from this state up to V2, some volume V2, it can, okay, while pressure remains constant. So you are going from Vi to V2, so that's why I have put V2 minus Vi. Okay, total work will be equal to W1 plus W2. In the similar way, in part C, you can also do the similar type of calculation. In this part, you do the adiabatic compression and then the cooling at constant volume. Try to do it by yourself. The rest of the calculation are also similar. Try to do these calculations by yourself. Now the next example is, you have a rigid tank which contains air at 500 kPa. So pressure is given while the temperature is 150. As a result of heat transfer to the surroundings, the temperature and pressure inside the tank drop to. So temperature becomes 65. This T2. This is T2. While pressure become 400 Kelvin. Okay, and you have to determine the work done during the process. So the solution is simple, and air is in the reagent tank is cooled and both pressure and temperature drop. The boundary work is to be determined. Okay, so you know that the rigid tank has constant volume. dV is 0. So if the dV is 0, so work will also become 0. The next question is, you have a frictional piston cylinder device which contains 10 pound of steam. So mass is 10 pound. At this 60 psi and the temperature is 320. Heat is not transferred to the steam until the temperature reaches, this is T2. So this one was T1 and this is T2. If the piston is not attached to the shaft and its mass is constant, determine the work. Okay, you have to find the work. Simply you will use this formula, W is equal to mPV2 minus V1. You know the value of pressure, which is 60 psi, mass is given 10 pound, V2 minus V1. So V2 and V1, because it is water, so for water you will use the steam tables. From the steam tables you will get the value of V1 and V2. So your answer, you will put their values here and your answer will be this. Okay, this is your answer. Example 4.3, a piston cylinder device initially contains this is initial volume 0.4 meter cube, pressure is 100 kPa and temperature, initial temperature is 80 degrees Celsius. Okay, the air is now compressed to 0.1, this is V2, in such a way that the temperature inside the cylinder remains constant. This is isothermal process. Determine the work done. So for isothermal process, you know that the W is equal to P1 V1 log of V2 over V1. So P1 is 100 kPa, V1 is 0.4 log of V2 over V1. So answer, you will get your answer here. Now I will solve the questions related to the efficiency. Okay, you first of all consider a 24 kilowatt okay, so consider a 24 kilowatt hooded electric open burner, this is burner, in an area where the unit cost of electricity and natural gas are 0.1 kilowatt hour, 0.1 dollar per kilowatt hour, and 1.2 dollar per therm. So one therm is equal to 105,500 kilojoule. Okay, so unit cost of electricity and the natural gas is given. So for electricity the cost is 0.1, while for the natural gas the cost is 1.2. The efficiency of the open burners can be taken to be 70% for the electric burners and 38% for the gas burners. Okay, so for the gas and for electric the efficiency is given. You have to determine the rate of energy consumption and the unit cost of utilized energy for both electric and gas burners. So formula for utilized utilized energy is energy input into the efficiency. Okay, utilize simply the efficiency is output over input. Simply it is out over in. Out means the energy which is utilized. Input is which is putting into the system, the energy putting into the system. Energy input is 2.4 kilowatt, okay, which is given here, and the efficiency of the electric burner is 0.73. Just put the values, you will get the energy utilized. Okay, and the cost of the utilized energy will be cost of the unit cost of the energy input is 0.1 dollar per kilowatt, which is given here, divided by efficiency is 0.73. You will get your answer. Okay, now for the burner for the gas. This I have calculated done this calculation for electric supply. So for gas, so Q utilized, which is for gas, the Q utilized is 1.75 kilowatt. This is 1.75 kilowatt, and the efficiency is 0.38 for the gas. So your answer will be equal to 4.61. Okay, so this is the rate of energy input, and the cost of utilized energy will be equal to cost of energy input divided by the efficiency. So energy input will be $1.2, which is given here for gas, divided by therm. So one therm is equal to 105 500 kilojoule. Just convert this into the kilowatt, you will get this answer, and divide it by efficiency, you will get this answer. This is not a very related example to your course, so I'm moving, this problem looks important. So consider an electric motor with a sharp power output of 20 kilowatt. Okay, so efficiency output power output is 20 kilowatt with an efficiency of 88%. Efficiency is 88%, and you have to determine the rate at which the motor dissipates heat to the room. Okay, you have to find the Q dissipated. It is to the room. It is in when the motor operates at full load. So motor is operating at full load. In the winter, this room is normally heated by a 2 kilowatt resistant heater. Determine if it is necessary to turn the heater on when the motor runs at full load. Okay, so we are assuming that motor is operating at the full load. The motor efficiency represents the fraction of electrical energy consumed by the motor that is converted into the mechanical work. Okay, I told you earlier, efficiency is output over input. So you are putting some electrical energy. If you are putting 100 joule of electrical energy, then there, if the efficiency of the motor is 88, then this electrical energy will be 88% converted into the mechanical work, while the 12 joule will be lost into lost as the work against friction, or it is lost as heat. Okay, so efficiency is 0.88. The formula is this: 1 minus efficiency into the electrical heat which is going into the system. Because I told you, you have to find the rate of determine the rate at which motor dissipate heat. Okay, so as efficiency 88%, while 12% will be lost, so that's why I have written 1 minus 0.8, which is 0.12. So 0.12 into 24, it will be equal to 2.4, which is larger than the rating of the heater, which is larger than this 2 kilowatt. Okay, so therefore heat dissipated by the motor alone is sufficient to heat the room in winter. So you don't need the heater. The question was that there is an electric motor in the room which is working. You have to determine the heat dissipated by this motor, because the efficiency is 88%, so 12% of the energy will be lost as heat. Okay, so in winter the room needs 2 kilowatt of resistant heater, while dissipation energy is 2.4, which is greater than 2. So you are getting enough heat from this motor, so you don't need to install any heater. This is also an important question. A geothermal pump is used to pump brine whose density is given at a rate of volumetric flow rate is given from a depth 200 200 meters. So pump is installed below, and it is putting some water from here to here, and the depth is 200 meter. Flow rate is also given 0.3 for a pump efficiency of 74%. So efficiency of the pump is 74. Determine the required power input to the pump. You have to find the electricity provided to the pump. Okay, so first of all you provide some electricity to the pump, and the efficiency tells you how much this electricity will be converted into the useful work, so that pump can push this water to the above here. Okay, so if the efficiency is 74, it means that if you are putting 100 joules of energy into the pump, then it can only utilize 74 joule of energy in order to push this water, and 26 will be lost against friction. Okay, so for a pump efficiency of 74%, determine the required power input to the power, disregard fraction losses in the pipe, and assume geothermal water at the depth 200 depth to be exposed to the atmosphere. Okay, so for this you have to put the water from here to here. So this is the mechanical energy will be equal to the potential energy. Okay, so potential energy is mg delta g. So m, you don't know the mass flow rate, while you know the volumetric flow rate. You know that m is equal to rho into volumetric flow rate. Volumetric flow rate is also given. Put the that's why here it is written rho v g into delta g. So rho is 1050, v is 0.3, g is 9.81, while delta is 200, because this difference is 200. You will get this answer. This is the unit converter. You can go through it by yourself. So w will be equal to, so electric work, you have to find the electric work. Mechanical work, you know, it is 618. Okay, this amount of energy you need, while the efficiency is 0.74, so you have to provide some extra energy. You need 608 kilowatt of energy to pump this water. Okay, while the efficiency of this pump is 74%. Okay, if you provide this 618 amount of energy to this pump, so you have to multiply this 618 with 74%. So pump is actually delivering less than 618 energy. Okay, so that's why you have to provide some extra energy. So you will divide your mechanical energy by the motor input. Okay, you have a room is which is cooled by circulating chilled water through a heat exchanger located in the room. Okay, the air is circulated through the heat exchanger by a zero point 0.2 horsepower fan. Typical efficiency of small electric motors driving is the efficiency is 54%. You have to determine the rate of heat supply by the fan motor assembly to the room. You have to find the heat. So shaft output is given. You know, efficiency is output over input. Output over input. Output is also given, which is 0.25 horsepower. In efficiency is also given 54%. Where heat supply, heat input you have to find. So heat input will be equal to output over efficiency. So output is 0.25, efficiency is 0.54. Just divide, you will get your answer. The water in a large tank is to be used to generate electricity by the installation of the hydraulic turbine generator at a location where the depth of the water is 50 meter. So depth is 50 meter. Water is coming here and to this turbine. This turbine is run, and the heat is generated through this generator. Electricity is generated through this generator. Efficiency of generator is 95%, and the water is supplied at 5000 per kg per second. Okay, if the electric power generator is made to be, so electric power generated is 1862 kilowatt and the generated efficiency is 95%. You have to determine the overall efficiency of turbine generator, mechanical efficiency of turbine, and the short power supplied by the turbine to the generator. First of all, you will apply the energy balance. So for applying the energy balance, E mechanical in minus E mechanical out will be equal to P over rho, which is equal to G into H. Okay, basically this formula is reduces to change in energy will be equal to GH. This is basically equal to the mechanical energy. G is potential energy. So 9.81 into 50. 50 is the depth. So just do the unit conversion, you will get your answer. Okay. Sorry. Here as you can see, we take the bottom of the lake as a reference. This is our reference. And then the kinetic and potential energy of the water are zero. So kinetic and potential energy, we are assuming it is zero. The mechanical energy of the water consists of pressure energy only. So P over rho only, which is equal to GH. So G is 9.81 while H is 50. Just put the values, you will get your answer. So this is energy per kilojoule per kg. While the flow rate is also given, just multiply this number by the flow rate, you will get your answer in kilowatt. Okay, so this is the energy. This is the mechanical energy which is of the fluid supplied to the turbine and overall efficiency begun. Okay, so this first of all, this water run here. This runs the turbine. So this turbine is producing this much amount of energy. Okay, divide 1862, which is the energy output. This is output energy and this is input. You will get your overall efficiency. So in the part B, you have to find the mechanical efficiency of the turbine. So turbine generator efficiency will be equal to efficiency of turbine into efficiency of generator. The efficiency of the turbine will be equal to efficiency of turbine generator divided by efficiency of the generator. Turbine generator efficiency is 0.676, which is calculated from here, divided by the efficiency of the generator. You will get your answer. While the shaft output and work will be equal to energy efficiency of the turbine into the mechanical energy of the fluid. So just multiply by these two terms, you will get your answer.